Hello. In this video, I'm going to explain problem 17 from the 2014 F equals MA contest. In this problem, we're told that a spherical cloud of dust in space has a uniform density rho naught and a radius r naught. And the gravitational acceleration of free fall on the surface of the cloud is g naught. And now, the cloud expands to a radius of 2r naught, and it'll still be uniform. So since the volume is the volume is 8 times as much, since the radius is double, the density must be 1/8 as much. And now we are asked to find the gravitational acceleration of free fall. Notice it's at a point r naught from the center, so it's not at the surface. It's at the same distance r naught. So, how will we do this? So to do this, we need to cite two main theorems, which it's exceedingly unlikely you would be able to prove this on the test itself or while taking it. So these are things that you should know by heart because they are pretty important. So basically they describe what happens when you have a spherical shell. If you have a spherical shell, then if you are inside, and it's a uniform spherical shell, the gravitational force is 0, and this is everywhere inside the shell. Now outside, the force will be the same as if it were as a point mass at the center with the same mass. Now, so basically what this means is that if you are outside the shell, you can just treat it as a point mass at the center for gravitational purposes, but if you're inside, the total force is 0, and that's no matter where you are, because the forces from the different parts of the shell will actually cancel out perfectly. So now, using this fact about a spherical shell, we can derive what will happen with a solid sphere, or a solid ball of mass. So now we have a solid ball. So suppose that we're outside. Well, remember that a solid ball is just a whole bunch of spherical shells. And so if we're outside, each shell acts like a point mass at the center. And since you're basically just adding up all of those shells, or in the continuum limit, integrating to form the force exerted by the entire solid ball, we end up just having that the entire ball acts like a point mass for the purposes of gravity. Now, how about if you're inside? Well, let's say let's say the total ball is radius big R, and now you're inside at a distance little r. Well, let's look at the different spherical shells. So spherical shells that are outside, so spherical shells of radius greater than r, will not contribute to the force at all, as we mentioned earlier from the theorem for hollow spheres. And the spherical shells of radius less than r will basically just act as point masses, because if you are at a distance r, you will be outside those spherical shells. And so basically, really, the gravity that you need to worry about is only is only the gravity from all the stuff inside. And now, how does this act? Well, remember that F is mg over r squared. And so let's say that's F at r. So I'm going to say m prime. That's just going to be the mass inside. And F at a distance r is going to be mg over capital R squared. But if you look at what is m prime, well, that's just the total mass times the ratio of the two volumes. And the ratio of the two volumes is just little r cubed over big R cubed. And thus we actually get that F at a certain radius r, where r is less than r, or little r is less than big R, is actually equal to mg over capital R squared times little r over big R. And so it actually equals the force that you would experience from the outside times the ratio of the distance from the center to the radius of the entire sphere. And so the force actually grows linearly with the radius inside the sphere. And so just to show a plot, this is not needed for the problem, but it just helps clarify things. Here is R, so this is hollow sphere, and then a solid sphere. For a hollow sphere, the force is 0 at first, and then at the radius, it reaches, mg over r squared, over capital R squared, and then it decays as 1 over r squared. That's proportional to 1 over r squared. And in the solid case, it'll grow linearly to that value and then decay as 1 over r squared. And that will be proportional to 1 over r squared. This will be linear, so it will be proportional to r. So that's what these cases look like. Now, going back to our original problem, what we can see is that this is basically a uniform solid ball, and if you're at a radius of r naught, well, what happens? Really only the mass that is inside contributes. And now how much mass is inside? Well, that's just 1/8 of the total mass. So you have 1/8 of the mass, but you have the same distance, because you're still r naught away from the center. And thus, remember that the gravitational acceleration is just the gravitational force divided by whatever your test mass is. And so the gravitational force is just the mass of the attracting object times the gravitational constant divided by the distance squared. And so since the distance is the same and the mass is the 1/8, the gravitational acceleration will be 1/8 as much. And so we get g naught over 8. All right. I hope that was helpful, and thank you for watching.